Thank you so much for invitation to this very nice workshop. My name is Yasuhiro Hatsugai from University of Tsukuba. Today, I'm going to tell you about the value-based correspondence for topological materials, and that's somehow related to the linking. Just I noticed this linking a few days ago, but let me explain that. That's like this. And H tells this kind of thing. If there is some system with a boundary, in some situation, there's some of the boundary flowing flow like this. That's H state, and that's related to the linking. That's I wanna tell you today. Okay. So plan of today's talk is like this. So let me explain a little bit about the topological phases, and also about the correspondence, and that's quite universal and applies to many phenomena. I will not introduce such diverse phenomena, and at the last part, I want to explain this link to this link. Okay, this is today's talk. Okay. So maybe it's not necessary to explain topological phases for some of them. Some of participants today. That's the related to Nobel Prize in 2016, and that's the discovery of the topological phenomena applied to the phase characterization. And before going into the topological phases, I would like to explain a little bit about the standard phase thing. Most of the phase characterization of physics today is related to the symmetry breaking. This is the example of the magnetic magnet. It's quite well known. And for the high temperature phase, the spin of each atom are random like this. But at low temperature, the orientation of the spin is ordered like this. So it's clearly different from this disordered phase and ordered phase like this. And that's characterized by some order parameter and the critical temperature like this. This is very much well known. And the most important thing of the symmetry breaking of this kind of continuous symmetry is that there is some low energy excitation by the disturbing this order parameter very slowly. And that's famous spin wave for this case. That's non-monochrome modes. And that's very important for the physical experiments, since if you apply some small perturbation, the system will fall. That's very important for the symmetric broken phase, like this. And for the topological phase, the situation is quite different. The key difference is that there is no low energy excitation like non-monochrome modes. So the system is gapped. So we cannot use this kind of low energy excitation for experiments. So the topological phase is the insulator. So we have to think a little bit differently. That's the idea. Okay. And so what we have to do is that we need to use something different. That's topology. And most of the famous example is the counterpole effect, like this. And it is the 2D system under the magnetic field. Let's think about some two-dimensional electronic system and apply magnetic field. And apply some current. Let's assume that there is some of the current flowing in this y direction. So due to the Lorentz force, there is some of the voltage appear for the perpendicular direction. And if this current is very strong, then voltage is also very large. So this current and voltage are proportional. And this proportional coefficient, that's the whole conductors. And the idea, this is the whole conductors. And the discovery by von Christing in this time is that this is quantized by this some universal constant. So it's very special thing, and the counterpole state is a gap, and the quantization is very high actually, and there should be some fundamental reason for this one. That's a theoretical motivation. And today, this integer quantized value has a topological meaning, And that's due to the Sarles Holmes Nightingale Dennis paper, like this one. And this integer equals tk and an integer, and it has some topological meaning. And let me explain this integer a little bit. So the system is, let's assume the system is two-dimensional system and with periodic potential. So there are some fundamental unit area like this. And let's write this pi as the exams passing through this unit area, like pi. And if I plot this one particular energy level as a function of this pi, is like this. This is very famous Hofstadter's back, right thing. And the normalized by flux quantum, this structure is periodic like this, and the quite interesting structure. That's actually a fractal. This is very well known. The idea, the discovery of this TK and N is that there should be some integer associated with this Hofstadter particle, right? And I put many integers plus and minus here. So for this fractal, the diagram, there's various integers. That means there's various phases. So the point is that if the Fermi energy of the fermionic system is rising this vacant area or the area, that's the energy gap. So the system is integer. System is like insulator, and that's topological invariant. So that's a topological, most famous topological figure. And there's plus and minus like this. So it means there's various phases. Okay. Then the point is that this integer has topological meaning. Okay. So, but I don't want to go into this detail so much today. But after the discovery by TKNL, there's some topological meanings that being classified, and that's known as the Chan number mathematically. And the physical meaning is that this Chan number is the total flux in some fictitious total flux in a brilliant zone. And that's related to the Berry connection. Berry is very close to the Berry phase, and that's related to the vector potential. That's this I denoted by A, and using this fictitious vector potential, if one calculates the total flux, that's given by this kind of thing. So the idea is that this kind of the integer is hidden in the material in some complicated way. That's the situation. And to be a little bit more, so let's think about the one particle Schrödinger equation like this, and it contains this state as a function of the momentum. But this K is the momentum in a crystal, so there's some periodicity, and I normalized by some number, and that's from -5 to 5 like this. So the idea is that due to this periodicity in the Brillouin zone, this two-dimensional Brillouin zone is kind of the torus like this. So this topological number is given by some fictitious fictitious flux in this Brillouin zone, and like this, and that's given by this kind of very connection thing. So that's a mathematics. But I don't want to go into so much detail, but that's the definition. So if one, so by solving this one particle Schrödinger equation, one can calculate some vector potential like this, and calculate this, and integrate over this torus over the torus, then one can get some integer, and that's used for the phase characterization. That's the idea by TKNNC. Okay. And another very special feature of the quantum Hall state is that there's some fundamental current near the boundary, because due to this the Lorentz force, the classical electron is moving like a circle like this. So the current associated with this kind of current in a bulk inside the system can be cancelled by cancelled by both directions. But after the near this boundary, this cancellation does not occur. So due to this magnetic field, there's some current is going near the boundary, and this current cannot be stopped by some impurity. Even if there's some impurity there, this current is always flowing like this. This is one-way going, so one cannot stop this current. So yeah, okay,
please.
Yeah.
Thank you for this explanation.
Yeah.
If the sample has grain boundaries or sort of internal walls, can you violate this? What happens in that case if I have a polycrystalline sample?
Okay, so if in that case, yes, domain boundary, both directions of the H should be there. So that should be cancelled. So the real boundary of the total material should be contributed to the total current H state per time.
So in a polycrystalline sample, the results would be modified.
Cannot be, the situation should be the same. Because near the boundary, the activity the domain should be there. So the H state for this domain and another domain should be counted. Yes.
Okay, but the current, the chiral current would still go through the system.
Still go through the system.
Thank you.
Okay, that's the situation. Okay, so the point is that this kind of H state can be very much fundamentally important, and I think that something related to this one. Okay, so what we have discussed a long time ago is that for conductance of the bulk and for conductance of the system with boundary should be the same. And due to this kind of constraint, one can get some mathematical formula. This left-hand side, since this is a Chan number or TK integer, that can be calculated with a boundary. And with boundary, there's some of the H state is there. So one can calculate this for conductance by some information from the H's. So bulk topological number and the H topological numbers are related. So the point is that this kind of the boundary state or surface state can be observed by experiments. So for the 2D surface case, one can see this kind of behavior of the H state by the angle of the emission spectroscopy and so on. So this right-hand side part is a real experiment, and the left-hand side, this is very good for theoretical calculation. That's the situation. So the theory and the experiments are related. That's the situation, and it can be very much important for the quantum effect. And today we noticed that applies to many phenomena, not only quantum systems. That I want to explain a little bit. Okay. So the point I want to say today is that topological phase is something very much special, a little bit different from the conventional order phase. And looks like there's no physical observable, but with boundary, there's something special occurs. And this something special near the boundary is observed by experiment. And the topological number is in some sense hidden. So, but it's very good to do some theoretical calculation, but may not be always related to the real experiment. But this H state and topological numbers are related. So calculating this topological number, one can predict some behavior of the H state. And experimentally observing this H state, one can know some topological information of the bulk. This relation can be very much universal for the topological phases. That's the situation. So the idea is that we discuss bulk by edges, and we discuss edges by bulk. That's the idea. So if as for the topological phase for the bulk, if one cuts the system, something occurs near the boundary, and one can get some information from the edges, and one can predict some bulk. And using this bulk, one can predict some behavior of the edge states that can be quite fundamental. So in this sense, edge states are the way to see topological phases of the bulk. And this can be applied for 1D system and 2D system and 3D system, and 3D system can be like this, and usual and the photon emission spectroscopy can be applied. So okay, that's a point. Okay, so I have explained this formula a little bit a few days ago, but I don't go into the detail, but the calculation is like this. So by I don't know explain this figure so much, but this gray area is the energy bar, and this line inside the gap is the H scale. The calculation is like this. So if one calculates this Chan number or T given integer for the gray area, that's minus 2 and plus 3. And the difference between this guy is the this 2 is the difference between above and below. So 0 minus plus 2 is minus 2. That gives Chan number of this bar, and this kind of thing. So if one knows yes.
Is there a typo in the second line? It looks like +2 minus
sorry.
should be 4.
This is minus 1 should be because this 2 is not. This should be a minus 1. Oh, sorry. Thank you. So 2 minus 1 is no.
Thank you.
This is minus 1 should be sorry. So this should be a particle over symmetry. Should be this should be minus 1. Yeah. Thank you for the correction. So okay, it's very simple, but this is really really true. That's the point I want to explain. I want to show. I want to say. So the original idea is the counterpole effect. So that should be a quantum effect. But it looks like this is not restricted to the quantum phenomena. That's the idea. That's the thing which we realized in this millennium. So the first idea is due to the Halden and Wu. They discussed something very much quite situation, similar situation for the photonic crystal. Photonic crystal is obeyed by a Maxwell equation. It's clearly a non-quantum. So this is a classical electromagnetic wave, but that if the system breaks time reversal, one can get something very similar situation to the counterpole effect. That's the idea by this paper. And this is really results for the really is by the experiment by MIT group just after the proposal. And this is the result. So originally this quantum the topological phase can be due to the quantum effect, but after in this millennium, we know this that to have this perfect correspondence, we don't need quantum mechanics. It can be a very much various phenomena. Okay. So one of the first example for this perfect correspondence is the mechanical thing. Just after the Halden paper, 2009, due to the program, they discussed some of the classical mechanical thing, microtube or something. And they discussed energy dispersion and found some the H state like this, and that's related to the Chan number of the bulk. This is the perfect correspondence for the Newton mechanics. That's the fourth thing. And the another example which we realized some time ago is a mechanical graphene thing. So by rotating this system, there's some Coriolis force. So that's the breaks time reversal. And then the situation is quite similar to the quantum Hall effect. And even for this spring mass system, one can get boundary localized mode, and that's governed by the bulk topological number. So Newton mechanics is okay, and Maxwell equation is also. And after that, so very much similar situation can be just realized in the electron EC circuit. So what can we recently realized that this perfect correspondence is even in EC circuits. And there's some boundary currents for the EC circuit. Okay. And a little bit more surprised that something very much similar is realized in some flow on the Earth. So because for the direction of the Coriolis force is reversed from the north hemisphere and south hemisphere, so the direction of the force is different reverse. So that clearly implies that the Coriolis force vanishes at the equator. So in this sense, equator is a boundary. So that's what pointed out by Delpress and the collaborators in this paper. So they discussed this, something topological thing on this Earth. So they predict some boundary state near the equators. That's actually very well-known geophysical flow, Kelvin wave and the analysis wave. Actually, this boundary mode is protected by the channel of the bulk of the geophysical phenomenon. Yeah, okay.
Historical question.
Yeah.
Lord Kelvin worked in the 19th century.
Okay.
And he knew about this stuff. He just didn't know to call it a Chern number or the waves are all there,
Yeah.
but it's just a novel perspective, perhaps.
Yeah, another symptom, right? Because Kelvin wave is very much well known.
Right.
Very established thing.
Right. So not 21st century, but 19th.
The 19th.
Thank you.
Maybe that's on a day, right?
Yeah, that's right.
So that's very known. So the point is that we can get another viewpoint topologically. That's the situation. So topological thing can be everywhere, but may not be that topological reason is not known. That's the situation. So that's very good thing for the topological phases. That's good idea, new idea to reinterpret well-known things. That should be a fun for at least for physicists. That's fun for me. So this is very good idea. Okay, thank you. So the point is that equatorial wave is topological. So today I want to go into the little bit link to this really that can be related to today's conference. That part. Okay, we are almost in the last part. Before going to that, one can do the same thing for the another thing. If one think about the game theory on the two-dimensional macroscopic coupled two-dimensional game theory, one can get some very much similar things by this I don't know. We took again in Japanese, so but yeah, rock scissors paper game. So actually there is some cycles on flow, right? Everybody knows that. So that's like a one directional rule, and so there's some for the game theory thing. There's some microscopic rule that breaks time reversal. And if one do the same thing for if one do some simulation for this couple thing, one can get some H state. Actually, this equation is mapped to the Kagome system on the inner magnetic field, actually, due to some linear the analysis like this. But I don't know into detail. But the point is that the H state is there even for the macroscopic coupled two-dimensional evolutionary game theory. So it looks like the bulk correspondence can be very much everywhere. So this is not the replicator dynamics. I'm not a specialist, but I'm not able to paper. So the summarize this bulk correspondence is that for the 2D thing, there are many things, and it's channel number and it's still validated. Looks like, and the phenomena itself can be well known. But we can understand this kind of phenomena topologically. That's the situation. And it's a fun. Looks like everywhere and the inverted. So the last part is the link to linking, which I want to explain today. So that's for the two-dimensional topological theory of superconductor. And we wrote very, let me explain a little bit about the very old paper. So we discussed Bongrego to Hamiltonian. That's a very known thing for physicists. So that's the mean field of Hamiltonian, and this is the energy dispersion, and delta is some order parameter. And for this superconducting business and triplet and singlet characterization due to the order parameter, symmetry of the order parameter. And this is the phase pathway energy dispersion, and this one, this vacant area. This is a two-dimensional plot of the energy dispersion. So there's some energy gap and gap closing and the energy gap like this. So this is a derivatives, and we discussed also for the called 2D triplet superconductor. This is gapless in some situation, and the order parameter is even quite like this. So I just noticed for this P-wave case, what can you do a little bit interesting thing? So the point is that the usual way to analyze topological business for the superconductor is just think about the 2x2 matrix, and this is has this kind of form, and it's very suitable to this discuss Bailey connection due to the Bailey, and this 2x2 is written by the like this. So we can parameterize this Hamiltonian momentum space by a three real number. That are the spatial three-dimensional spatial vector R. And if one starts from very phase channel by expression due to the Bailey connection like this, one can rewrite this thing by this by using the R vector. That's a Skamian number like this, and that we wrote this number thing a long time ago, and everybody uses this kind of Skamian number thing. But the very special point for the P-wave situation is that this order parameter and the momentum is separated into the x part, kx part, and the ky part like this. Kx and ky are separated. So this is due to the P-wave symmetry or some situation. Anyway, for this model, this R vector has the x of the kx parameter and minus divided, so just minus y vector of the ky. So for this Skamian number is written by this kind of thing. This is just a Gauss linking in there. It's a very more thing. And the momentum is kx and ky are separated. So this linking number is the loop of the kx loop and the loop of the ky. So not kx and this is ky. So the linking number of the kx and fkx and lky is each number. That's the point I want to show you. So let me show some examples. For this P-wave case, I did a small calculation by Mathematica a few days ago, and just produce that. So this is the energy dispersion by changing the chemical potential. So if I put the chemical potential -1 for this parameter, kx loop and ky loop is clearly linked, and this channel number is 1. That's given by a linking number. And at a critical point, these two loops cut each other, and linking number is not very defined. But if one put the chemical potential far away from 0, then it's politically trivial situation. Then in that case, the two loops are separated, and the channel number is 0. That's linking number 0. So this is a trivial superconductor, and for this linked case, usual understanding that this is a topologically non-trivial P-wave superconductor. And that implies that there should be a topological edge state if the system has boundary. And this edge state should be experimentally accessible. So the point is that by observing this edge state of the P-wave superconductor, first experiment says that they observe some non-trivial links. Okay, that's the main point. But I want to say today. So this is a summary page. So today I have explained a little bit about the topological phases and package correspondence, which we use for this period. And at the last part, I have some links, and that will be experiment that you have to. Okay, thank you.